So thanks a lot for joining. You've seen what this session is about when you signed up, so I don't want to waste too much time repeating what you already know. Just very briefly, solar and wind power are rapidly growing in importance, and of course we have reason to believe that they'll form the backbone of the clean energy system. And so for that reason, energy modelers, meteorologists, and climate scientists have increasingly started working together on understanding and addressing current and future variability of these renewable generation technologies. And in this session, we want to take stock of this research area, of this very interdisciplinary area, and look at where there's still room for improvement, where open questions remain, for research going forward to support decision-making on rapid adoption of climate neutrality, both in the EU and internationally beyond. So what we're going to do is we're going to start with 3 brief talks from 3 speakers who I will introduce in a moment. And after each talk, we'll have time for a brief question or 2. And to manage the questions, we're going to use a tool called Slido. And Bryn Pickering, who's helping us run the session, is going to show you just now how that works. Great, thanks a lot, Bryn. Right, so let's get going. And let me introduce our first speaker, Tim Trendle. Tim is a researcher at the Institute for Advanced Sustainability Studies in Potsdam, where he analyzes European energy policy, in particular the implications and trade-offs of different possible pathways to a fully decarbonized energy supply. And to do that, he uses energy system models with high-resolution data on renewables. So to start us off, Tim is going to talk about some recent insights from this type of modeling and some opportunities for further expanding it. Tim, the floor is yours.
Thank you, Stefan. So yeah, basically what I want to show you are some key insights that we gained from applying a model that is spatially and temporally highly resolved, just to give you an idea of what can be done with these kinds of models. And my talk, the context of my talk will basically be on electricity infrastructure, supply and electricity infrastructure in Europe. As you may or may not know, Europe is currently generating roughly 30% of its electricity from renewable sources, but is also aiming to reach 100% or nearly 100%. So a future in Europe will likely look like this, where the current solar and wind capacities are expanded by factors 5 to 6, or even more if the electricity demand is increasing. So this is a huge expansion of the current capacity that exists today. And the question that arises from here is where to build all this infrastructure. And that is an important question because it has impacts on many aspects. For example, on landscapes, on cost, on energy dependency, on the ownership structure, so who can invest and who will invest. And so we try to tackle this question. We try to find answers or at least assess these impacts so that others can find an answer to that question, like politicians basically can find an answer to this question. And to be able to assess these impacts, we needed models with high spatial and temporal resolution. So we built models, such models. And basically what we did is we built 2 things. The first is a estimation of the renewable generation potential in Europe for all municipalities in Europe. So there are roughly 120,000 municipalities, and for each of these municipalities, we can estimate solar and wind generation, or the max solar and wind generation in that municipality. And on top of that, we built a model that is also highly resolved in space, but also highly resolved in time. We called it Eurocal IP, and that model is able additionally to capture fluctuations of renewable generation. And so using these models, as I said, we try to assess impacts of the location of electricity infrastructure. And one of the ideas that exists in Europe is this idea of self-sufficiency, where the location of supply infrastructure would be the location of demand. So supply is located where electricity is actually used. And we asked ourselves the question, is that at all possible? in Europe? And is it possible for Europe as a whole, as a continent? Is it possible for individual countries? Is it possible for individual regions? And is it possible for single municipalities in Europe? And this idea of whether it's possible or not, basically what we did is we said, as a necessary condition, the generation potential must be higher than the demand. If the generation potential is below demand, it's certainly not possible in that area. And what you see here is the result for these 4 layers that I was talking about. Now I show you 2 of them in more detail. The first is this continental layer. So in here, Europe as a continent is self-sufficient, and you see this entirely green map telling you that yes, that is possible. So what this means is Europe doesn't have to import electricity if it doesn't want to. It can power itself with electricity from sun and wind. But then if I move down to the municipal layer, in which municipalities, each municipality tries to be self-sufficient, you see these red dots all over Europe. So these are the municipalities where it is not possible. The generation potential is below electricity demand. So here certainly self-sufficiency doesn't work. Still, you see that the largest part of that map is green. So for the largest part of Europe, self-sufficiency on the municipal layer still is possible. Okay, so this is one of the things we could find out with this model. It is highly resolved in space, but we could also show a trade-off that comes with the idea of self-sufficiency, and that is the geographic concentration of supply infrastructure. So if you're locating supply infrastructure where demand is, of course you're concentrating it in locations with high demand, and that's not a problem for small cities or villages, but for a metropolitan area like Paris, this can be a problem because you're adding stress to the land that is already very dense and very has a lot of stress already. So this is a trade-off that comes with self-sufficiency that you have to accept if you want to go for self-sufficiency. Now, a second thing we showed was the cost of self-sufficiency. What would it cost to become self-sufficient in Europe? And what would be the differences on these levels that I was talking about, continental level and country level and regional level? And the results are here. And the first result is actually not very surprising. The first result tells you that the lowest cost option is a continental supply where supply infrastructure can be located anywhere in Europe. So it can use the best locations with best wind speeds, best solar irradiation, and that leads to lowest cost. And that's actually not a surprising result. That's kind of what you expect. But then when we enforce country self-sufficiency, so national self-sufficiency, you see how the costs are increasing, and they're increasing even further if regions try to be self-sufficient. But this 21% that you see here, this case of the regional supply, is a case where there's still a continental power grid that can be used to balance fluctuations, right? So actually, it's not full self-sufficiency, it's rather net self-sufficiency. The supply is within the region, but the fluctuations of that supply can be handled anywhere in Europe through trade. Now, if we prohibit this trade as well, and we prohibit trade between countries, you see how costs increase. And if we prohibit trade between regions as well, you see how costs increase even further. And now what all of this tells you is that the location of supply infrastructure is, of course, increasing cost, but it's not a major cost driver. It increases costs roughly by 20%. What's more important is the location of the balancing infrastructure and also the way balancing works. And by balancing, I mean things like storage, battery storages, or hydrogen storages, and the like. So supply location is not as important as the balancing location. So I told you that the continental supply has least cost, and again, this is not a very surprising result, but we can also show a trade-off that comes with this idea, with a system that is built based on the idea of least cost. This system also has a geographic concentration of the infrastructure, but this time at the best locations. So you see these dark red dots on that map. These are the locations where the most of the electricity is generated. And so they have a lot of supply infrastructure within the region. And on the other end of the kind of chain, you see all of these blue regions that import a large part or all of their electricity. And so they're strongly dependent on their trading partners. And both of these things you can consider as trade-offs that come with this notion of a least cost system. Good, so that's basically all I wanted to show you as some of the insights we gained with a model with high spatial and temporal resolution. Basically, the benefits of these models are, so of course they increase the fidelity of scenarios with high shares of renewable energy, with high shares of renewable electricity in this case. And also they allow you to assess impacts that are relevant to the local population by being spatially explicit. So by having this high spatial resolution, we can assess impacts that are relevant locally. And the challenge that comes with a model like this, and that will potentially even get bigger in the future, is that it increases, of course, the model complexity. So we are adding high spatial and temporal resolution that we want because of the high shares of renewable electricity, but we're also adding more sectors. We have parametric uncertainty in the models. We have the variability of climate. We have trends in climate, so things like climate change. And we're adding all of these things to the models. Of course, we don't always have to add all of these things, but adding those increases, of course, the complexity of the models, and we have to be able to deal with this complexity. But on the flip side, it's of course also an opportunity because it allows us to answer more research questions that we couldn't answer before. And the foundation of all of this is, or an important foundation of all of this is input that we get from climate science. And that is also the topic of the subgroup that we will be discussing later on. But for now, I want to thank you for your attention.
Great, thanks a lot, Tim. Perfectly on time as well, making up for some of the time we lost in getting the session started. We have a couple of questions that have come in, and we're just gonna go for the most upvoted one, and we'll see how we stand time-wise after everybody has spoken, whether we can allow some more questions or whether we have to go for those in the subgroups. So the most upvoted one right now is from Gabriel on how, and he's asking, how is the model spatially disaggregating demand from national totals?
That works mainly based on population counts, but also based on the location of industry. So what this means is that, so we have a database of at least the largest industrial plants in Europe, and an estimation of their electricity demand. That's what we subtract from the national data. And then we use the population count as a proxy, not only for households, but also for commercials, saying that commercials are equally distributed in the country, to then disaggregate the rest of the electricity demand.
Okay, great, thanks a lot. I guess we don't have an opportunity to easily check whether or not that answers the question, so we'll just assume it has. Thanks again, Tim. So
Thanks.
Our next speaker is Alberto Troccoli. Alberto is a professor at the University of East Anglia. He's also, and more importantly for our purposes, the co-founder and managing director of the World Energy Meteorology Council. So he very much knows about all the ins and outs of getting energy and meteorology communities working together. And he spent time at institutions like NASA, the ECEMF, CSIRO, has led a range of international research projects dealing with how to use weather and climate data for improved decision-making and risk management. And today, he's going to show us in particular the range of energy relevant data already available through the Copernicus Climate Change Service. Alberto, the floor is yours.
Okay, thank you very much, Stefan, for the introduction and the kind invitation to speak at this event. If you want, I can switch on the camera. Should I? Okay, so you can see me. And all right, so I was given about 8 minutes to present all the work we've done here on C3S Energy. So it's a Copernicus Climate Change Service for energy, which is operational, and yeah, it's going to be a challenge. So I'm probably going to take about 30 minutes to cover everything. Well, not everything, just to scratch the surface. So allow me to take this time to go a bit in detail here. So team discussed about the complexity of the system when you start to introduce climate issues, and that's exactly what we've tried to address here. So what we have been working on is a system that works for both the climate and energy, and we've done that by talking a lot. We've done many workshops where we interviewed and interacted with energy sector people and find out what could be useful from a climate perspective. So this process has started many years ago, and the main thing that we've highlighted here is that we want to talk in terms of energy units, energy in the sense of power, not the energy, solar energy or so. But that's the key element. I think that's one of the key kind of juncture between the two sectors. Traditionally, climate has talked a lot about capacity factors, which is good. I mean, it's obviously that's needed. But to go a step further actually requires quite a lot of effort because, yeah, we need to learn about energy data, so the language the energy community uses, where they get the data from, and all the issues that come with that. So we've done a lot of that work and interaction, and I think we've come a long way since we started. You can tell me. Anyway, so that's the basis, and this is basically in a nutshell what we've been developing. It's a simplified kind of diagram, maybe still too complex, but in essence, we are dealing with 3 timescales. So in time, so we look at what happened in the past for the last about 40 years, say, and then we look at what happens in the near future with seasonal forecasts. So the past is with typically with the reanalysis product. Seasonal forecasts then are used for the kind of present, and then future, we look at the future with climate projection. So we cover quite a long range of timescales, and the purpose really is to isolate the role of climate and all the complexity that is energy. So obviously energy has a lot of factors that contribute to the why there's demand is such and such, and from country to country varies and so on. So our role is not to understand all the social aspects or technological aspects. It's more how we can isolate the climate. So that's a key aspect of what we do. And we start by taking the best climate data we can. So we look at that and try to improve it where we can. Sometimes there are biases and errors and so on. So we do quality control on the climate first, and then we convert that into electricity. So here also we talk about energy, but at the moment it's mainly electricity, like with Tim, I think. And so we look at electricity demand, wind power production, both onshore, offshore, PV production, only PV for now, given the predominance of PV, and then hydropower also, both run of river and reservoir, not the pumped hydro, because it's yeah, the input from climate is very marginal in that case. So we don't want to enter in that kind of modeling. So we produce all these indicators, both for climate and energy, for this 3 timescales. So there's quite a complex data system behind this. and it's all done operational. Now I'll show you later a bit what the engine of this looks like, just to give you a flavor of that. What I'm going to do here, instead of covering everything, I wanted to give you a bit of a background about how we developed and produced all this data, starting from the energy. So I skip the climate. I don't know if it's a good thing for this conference, but it's too late now to change. So climate, we know is pretty good. I mean, obviously, if you talk about seasonal forecast, the scale is what it is, particularly for Europe, but there are improvements nowadays. So also for projections, there's no way to check whether they're good or not. So we trust them. But of course, we do a lot of work with them. We try, as I said, to bias correct. So taking the climate data as a given for this talk, what we do then is we use different methodologies for different type of energy indicators. So for electricity demand, we use models. It's a statistical model based on GAMS, so generalized additive model, and it's only done at this stage for national averages. And I should also have said that everything at the moment here is done for Europe, but there are plans also to extend beyond Europe for future developments of C3S energy. So let's focus on Europe, and most of I think the attendees are from Europe anyway, so that's not a big problem for this audience. So the electricity demand, we said, is a statistical model, and I'll show you some of the results in a minute. Then for generation, we have wind, which is a very standard model, wind power, so it's physical model. For solar power, we have a mix of, so it's a model, a single model, but it's a mix of statistical and physical models, and it's quite elaborated. So there's, it's not so simple to explain here, but it's done by group at Armin, and I also take the opportunity to acknowledge and thank all the contributors to C3S Energy. So at the bottom you see the contributors. The World Energy Meteorology Council is the lead of the development of the service, and then CA, IPSL in France, Meteor France, EDF, Met Office, Armin, or Paris Mines Tech in south of France. And lastly, for hydropower, we have also a statistical model, which is a random forest model, and is done, as I said, for the two models, the two types of hydropower, run-of-river and reservoir. Okay, so let's look a bit at the results here. These are just to show you how good the models are. And then once we have validated these models, we produce for all the indicators, there are time series available for each country for the periods I said. So you won't see the time series here, but imagine that that comes out of that. But first of all, we want to be sure that what we do in terms of energy is reasonable enough. It's not excellent, but it's considering that we are doing for the whole of Europe, the data is what it is in some cases. I think the results are pretty good. So take France for example, here in the middle. It's this country where we got the best data, and you can see also from the modeling that is very, very good. It's correlation close to 1, and it's the results are based on this model, which is very, very similar to what is used operationally also by EDF, and actually the model was developed by EDF as well. But there are countries like Luxembourg, for example, where the results are less good, and they are also dependent on the months of the year. The colors represent the months of the year. So where you don't see a straight line, it means that results are not so good, but still the correlations are okay. But overall, we are all 0.9, close to 1 in many cases. So this, we are pretty happy with the model so far. And what we've done, again, just to reiterate, is not trying to model the demand as it is. We actually remove all the other what we call confounding factors for climate. So we remove what we know is related to GDP, for example, and try to isolate the role of climate. And then we use indicators from climate like temperature, solar radiation, wind, and humidity. So there are various factors from climate. Of course, temperature is the most important one, but also the others are relevant. Okay, so moving on, wind, we got reasonable results, particularly for Northern Europe, for Southern Europe, well, Italy particularly, and Switzerland not so good. One of the main reasons here is that we haven't specialized the model to tell it that you shouldn't build a wind farm on the Apennines or on the Alps, for example. So that's another one thing that we want to do, is to remove areas. It's pretty straightforward, of course, but we, in this case, we want to have a uniform approach, and now and the next stage probably will be more selective about the areas where we put the wind farms, because at the moment they're all scattered at each point. But with the model we produced, you have the data at each grid point, which is 25 kilometers by 25 kilometers. So you can, in principle, look at that, and we are validating here only the country averages. So for wind and solar, we have the gridded products. For demand and for hydropower, we've done it at national level. Okay, solar, similar to wind, is pretty good in most places, but particularly Germany, where the model was first tested and developed. France starts to diverge a bit, but then you look at Switzerland, for example, same problem with that I mentioned for wind, and you can see the scatter starting to become larger. Yeah, as I said, overall, I think we are pretty satisfied. And again, without going into much details, we have similar results for hydropower, for the reservoir at the top and the run-of river at the bottom, for all the countries where there is enough hydropower to talk about and model, and where we have, of course, the data from production. And I should have also mentioned that the data, most of the data here comes from the ENSTO-E transparency portal, and so we've been also working closely with ENSTO-E to understand some of the issues there, and managed to resolve most of them, but still there are some. We had places, for example, here for hydropower, where we had a capacity factor greater than 1. So obviously there was some issues there, so that I think that yeah, we resolved that, but yeah, sometimes you have to be careful with what you get from the data. So overall, yeah, we got good validation of the models. So of course we know there are improvements, as I said, particularly for wind and solar. We know we need to isolate some of the areas. For demand also, there is work to do, and same for hydropower. Hydropower, by the way, we model it using temperature and precipitation, and that showed to be a very good model, good predictors. Of course, it's not temperature and precipitation by themselves, like instantaneous values or averages over short periods. You have to look at accumulating, for example, precipitation over quite a long period. It could be a month, it could be 3 months or more, and we've done that calibration depending on the country. So each country will have its own kind of indicator, its own averaging period, depending on the features that are in that country and that are picked up by the statistical model. Okay, so I said I was going to show also what's under the bonnet of this system, and of course, it's not all it is. There's much more. You know, there is a scheduler, there is all the other things, but basically there is quite a complex system behind to make this service operational, and that's basically run every month. We update all the indicators that need to be updated, including the reanalysis of the historical data, and then a seasonal forecast every month. The projections are updated every year also, so they don't need to be updated so frequently. But this is done, as I said, automatically, following a quite rigid schematic and a set of scripts that we got. So that's it. But on top of that, we also have quite a bit of communication and documentation. So we've done tech blogs, run webinars to explain how we build this system. Some of you might have already followed them. Advisory board was helping us also with the development, and now we've got also quite a rich documentation with the variable fact sheets, data quality assessment, methods and limitations, bias adjustment, user guide for seasonal forecasting. So they're more technical kind of issues that come from climate that are not always so digestible. And so we try to make that as easy and approachable as possible. But of course, yeah, there's quite a lot of complexity, and we can always improve. If you have, you know, feedback and you want to know more, please get in touch. We're happy to develop things that, yeah, they are. We want to explain better. We also have done case studies. I haven't touched here, but we also had, as part of the service, a couple of case studies and also key messages. There's FAQs, tutorial videos, blogs, team stories, and you can find most of these things on C3S website. Some of it is not uploaded yet, and so you can still go to our old kind of websites, which are the demonstrators that were developed for the previous version of the energy service. So we got two. One is ESM at the top here, is still alive, and you can get quite a lot of data there. You can play around, a lot of combinations of climate and energy data. You can download the data, you can download the plots, you can do, and actually, yeah, we've done quite a bit of work on that, produced some papers and several other things. And also the other the demonstrator is the one at the bottom. It's C4E, Clean for Energy, also developed. There were two parallel projects going on, and now we got a new visualization tool that is coming up, and it will be hosted by C3S on. So the ECMWF maintains this. And in the meantime, we also developed a separate tool more for educational purposes, but we found that actually this is useful also for general communication with technical people, because it's easier to approach. The visual side is easier, maybe more pleasing, going from what some people say. But it contains this one, for example. If you go to this website, it contains most of the material and the data that are available on the ESM demonstrator, just in different formats. And again, this is live, you can look at this. And now we are working on the next generation also, which is global. So we are going to launch the global version of this very soon. So watch this space, and you can just look at our Twitter or website at wemcouncil.org. So I think that concludes my talk. I managed to stay under the 30 minutes that I threatened you to be awake for, but maybe you've already fallen asleep, or maybe hopefully not, because we've got a great talk coming up after me from David. And I just want to give you the website. I think you can also have the presentation later. But there are two talks coming tomorrow, two posters. I encourage you to have a look at those. One by Laurent Dubu, who is going to go a little deeper on the energy indicators that I talked about today. And also Hannah Bloomfield, who got a very nice paper using the data we produced with C3S Energy, looking at projections and various scenarios and so on. I won't steal the thunder, so I'll leave it at that. And thank you very much for your attention.
Great, thanks a lot, Alberto, for this talk. I'm just going to have a quick look at the questions. There's one, the highest voted one currently. Are you going to use machine learning or any other sophisticated techniques in order to train your data set?
Okay, yeah. So yeah, machine learning is sometimes, I mean, in my world, is a bit overused. But if we yeah, machine learning, basically, that's what we're using for hydropower modeling. So I said random forest is what we use, and that classifies as random forest. Of course, we could spend more time and improve things, and we'll likely do that. But like in the case of demand, I think the experts at EDF try to use different methodologies, and they found that ultimately relatively simple model like GAM was good enough for the purpose. And so yeah, there is a host for courses, I guess, and yeah, you can play around. You have to balance, time you spend on machine learning and so on. But like for solar power, yeah, I know it could be used, but we're looking at climatic timescales, which is not the same as short time forecast. So it's for short time forecast, I've used it also in the past. Machine learning is fine, but in this case, we need to base it more on physical grounds and a little bit of statistics as well. Wind power is different. It's difficult to see how machine learning could really add too much value, but again, worth testing. And yeah, that's it, I think.
Okay, great. Thanks a lot. Other questions can be dealt with later in the groups. So for now, let's move on to David Brayshaw. David is Associate Professor in Climate Science and Energy Meteorology at the University of Reading, and he leads the Energy Meteorology group there. And the research in that group is really on understanding the impact of weather and climate on the energy sector, and to develop new ways to exploit this understanding for the benefit of improved risk management and planning for energy. So David's going to talk to us about some of the current critical questions at this intersection of weather, climate, and energy models emerging from his own work, and maybe also share some insights from a recent workshop he co-organized for the Primavera H2020 project on exactly this topic. So David, thanks a lot, and the floor is yours.
So thank you. Sorry, I missed some of the change over there. So I work in the meteorology department at the University of Reading, which is one of the largest research departments concentrating on the fundamentals of weather and climate in the world. And like many of my colleagues, I have a physics and climate science background. Though for the last decade or so, I've been working a lot on the use of that weather and climate information for energy applications. And through that, I've been able to work with the UK TSO, National Grid, various energy traders, but also a series of fairly large-scale programs such as the Primavera Climate Model Development Program, S2S4E. Alberto's already mentioned the ESEM project, which is one of the predecessors of C3S Energy. And as a result of kind of being quite involved in the use of weather and climate information, but energy is still kind of a second scientific language to me. And I think this concept of language is one I want to come back to a bit, because it's one of the key barriers, I think, to the interaction between our two communities, is the lack of a common language there. So I'm not here to sell you a particular data set or a particular model or a particular product that we've produced. I can point to several on our website that we've been developing and using over the last several years. What I want to do instead here is sort of take a bit of a step back and try and focus on what I believe to be some of the kind of the bigger issues with this interface between the weather and climate on the one hand, and the use of that information in energy modeling to solve energy problems on the other. So yeah, I don't want to spend too long on this, but I mean, the background of this is the energy sector has always been exposed to weather and climate since time began. It's been exposed to extremes and fluctuations in demand, but with a rapidly changing climate, with a thrust to decarbonisation, so a growing dependence on the use of renewable generation, and as a result of that, we're actually increasing the exposure of that energy system to climate variations, to weather and climate. Renewables depend, by and large, certainly wind and solar, depend a lot on weather. Now, historically, there have been quite weak connections between these two research fields, so it seems to me very timely that projects such as this are building these bridges to start to anticipate the impacts of climate on energy into the future. So that's changing wind and solar patterns, changing extreme weather that damages infrastructure, and so on. But also, an area that often gets a little bit more overlooked is to try and ensure that when we do energy system modeling, that the solutions that are produced are robust to the fact that climate is also changing. And this was kind of behind the motivation of running this workshop back in June. I don't know if many of you may have already been there, in which case I apologize, these slides have a very strong overlap with the ones I gave at that workshop. But we were attended by 70 to 80 people, it was online, and we gathered a lot of thoughts and ideas about what the next challenges are for this field. And I encourage people to have a look at it. So we wrote a brief report on this, which is in press at the moment for the Bulletin of the American MetSoc. And this talk kind of presents some of the results and thinking from that workshop. So today I'm going to focus on one particular aspect, and I think it chimes with the interests of a fairly large group here, which is the idea of characterizing climate risk in power system planning. And by that, I generally mean generation expansion planning, transmission expansion planning, rather than sort of integrated assessment models, and not dabbling too much with operations and trading here. But I'm very happy to discuss those other areas offline. But the reason why I'm focusing on this, well, why does climate matter to energy? The prevailing viewpoint, certainly in my community, tends to come from the idea of a physical energy system and whether it is able to cope with climate changes and variations. So it often boils down to the idea of stress events. So it could be damaging weather extremes. So some storm comes along and knocks over all the pylons or floods a substation, or it comes down to compound events. So periods of low wind, high demand that kind of cause residual load on the rest of the power system to be very high. So can we cope? Can we keep the lights on during this low wind cold snap? And that's what a lot of work's boiled around to. But what I'm going to focus on here a little bit more is the idea of these robustness of energy system modeling solutions, particularly think about the kind of these optimizations of how much of which type of renewables we should build into the future. How robust are they to climate uncertainty? So, as I say, this is kind of my second language, but my cartoon picture of that is you have some sort of historic weather data which informs your resource potentials and your demand for heating, for example. So there's some sort of weather sensitive ingredients of the power system. There are some conventional ingredients, so conventional power plants, transmission resources, and many other inputs around policy choices, economic choices, technologies that are coming available. They're fed into some sort of planning model, and it out pops some sort of solution which tells us something about where and when to build wind capacity, transmission capacity, various different types of other conventional resources. It gives us a solution of what the lowest cost usually system should look like. The issues with that from the climate perspective is, well, at its heart, that operation, that planning model is often very expensive, and it's very difficult to run very large, very long simulations with it. So as a result, a lot of the inputs that have gone into those, in terms of the weather sensitive parts, tend to be orientated around very limited duration data sets, often just a couple of years long. And then that brings up the question that we know climate, from my side, we know climate is variable from year to year, from decade to decade, and we know there's a changing climate into the future. That brings up the question, are the solutions, these estimated capacities of these different resources, are they robust to the sampling of that weather data? And the short answer to that is that they're probably not, particularly if we're just dealing with individual one-year simulations of weather that are fed into these planning models. So the plot on the middle there shows results from, it's a very simple planning model. It's a single zone copper plate made to look a bit like the UK, but doesn't really matter the details. But essentially it's allowed to build 4 different technologies: base load, mid-merit, peaking, and wind power. We've asked it to estimate the optimal capacities given some weather inputs for demand and for wind power generation potential. And what you see in the bar chart there is that in each of the bars, focused on the wind one, is if we give it a single year of weather data, we can estimate that the optimum amount of wind power to build should be up to 35 gigawatts, or as little as 2 gigawatts, 1 gigawatt. So there's a huge range if you just pick that 1 year. If you pick a bad year, you're going to be miles off the kind of the average weather, if you like, the average solution. There's a further problem that even if you ran that model, it reviews, I think about 35 years of weather data are fed into this. If we run the model 35 individual times and calculate the average installed capacity across those 35 individual solutions, we get an average about 20 gigawatts, the center of this white line in the center of the bar, which is still wrong when you compare it against the ideal optimum solution, if you like, which is if you were to solve the model over the whole period, give it all 35 years of data all at once, where it would actually build 17 gigawatts. So the idea that 1 or 2 years worth of weather data thrown into a power system model gives you a robust solution, if you like, from the climate perspective, I think is a little bit questionable now. And I think it's really good that we seem to be kind of starting to progress beyond that as a community. But then this part, we've only dealt there with historic weather data. This uses a reanalysis products. There's many available, and there's a growing industry in converting reanalysis products into meteorological reanalysis products into energy reanalysis now. But that begs the question of, well, what happens with future climate? And the uncertainty around what future climate means for energy system planning is only really just beginning to explore. And this is partly one of the reasons why I'm very excited to be here, is to hear more about projects that are beginning to do that, Plan for Us and others within this space. But there's so many degrees of uncertainty here. That there's the climate forcing, how much greenhouse gas emissions are there going to be? What's the response of the climate system to those greenhouse gases? And how do we sample that? The climate varies naturally from one year to the next and one decade to the next. So picking random snapshots of that, you know, even 10, 20-year snapshots, you can actually end up with quite biased results relative to the true long-term average. And that then also glosses over a whole another layer of complexity, which is about regional and seasonal diversity. So I just want to focus on the bottom two rows of plots here. So these are plots that come from the ESM demonstrator, the one Alberto mentioned, and looks at differences in residual demand, so demand net wind across Europe for different countries, taken projections for the change in demand net renewables between 2050 and 1990 from 2 different GCMs. And hopefully you see that the patterns on this bottom row here for the annual average, the winter average, and the summer average are quite different. So different climate models are giving you very different answers, or it could be that we're sampling just random different decades, but there's a huge degree of uncertainty when we start to drill down into seasonal changes and country level changes and lower. Added to that still, there's also, I don't think we really understand the mechanisms controlling changes in surface wind speed, change in surface solar radiation yet. I think there's a lot of work to do on the fundamentals of the climate side that we need to understand how these things are being driven. So there's the data, yes, but we also need to kind of understand the data and what it's telling us and understand these forms of uncertainties that are being presented there. The good news, however, is that we're more able to do this than we have ever been in the past. There are numerous different realities. These are 3D reconstructions of the atmospheric circulation of the last 30, 40, 50, 100 years. There are numerous different ones out there. We have climate models that are getting ever better, both for short-term forecast, by short-term I mean weeks and months ahead, out to decades ahead, out to end of the century, that they're getting increasingly good. And there's huge international efforts about kind of carefully designing how the experiments should be formed, standardizing the data, making it available. And there's a growing amount of high frequency data there that's really suitable for detailed power system planning there. So that's the good news, and that is a massive effort amongst the climate side of the community. And the good news is that's then translating into progress. So these primary estimates of renewables demand, hydropower, so on, are becoming increasingly common, and it's carrying through into stress event characterization, forecasting, system design. And a really encouraging result is we're beginning to see GCM climate model data being used in power system planning. So this is one of my favorite papers at the moment by colleagues at NREL, Michael Craig and others. They drove a complex power system model, a unit commitment economic dispatch model of Texas by climate data from 5 different GCMs, 5 different climate models. And they assessed how much of different types of generation resource will be used under a future climate compared to present day. And this was their result. So coal, gas, nuclear, wind, solar. You can see the 5 different bars give slightly different answers, but they're starting to study what the impacts are across multiple different possible climate futures, which is great. But there's so many challenges that we haven't yet even begun to scratch the surface on. Picking again on this paper, which I do think is a very good paper, one of the highlights of that result was for this particular region, they showed that there'll be less call for nuclear power because all 5 GCMs agree. But when you actually look at the details, one of those GCMs is giving you a massive increase in coal use, whereas the other 4 are giving you a massive decrease. So to me, that calls the question of why is that one model doing something very different? Why is that the energy model is identical? Why is that climate model, why is that climate data giving us one very different response? And how does that affect our confidence in the fact that nuclear is predicted to decrease? So I think we need to kind of start unpacking some of this stuff. The second, another example of this is comes from Hannah's work. So in my own group, the fact that we're building new energy systems, we recall a lot of this kind of boils down to, a lot of the main thinking comes down to kind of stress events and how likely we are to get stress events in the future. The point is, as we're changing the power system, we also change its weather sensitivity. So this is the bottom plot, shows the correlation between residual demand in the UK versus the amount of wind power capacity we've built. And in 2008, we had very little wind power capacity built. And essentially, the dominant response was down to temperature. If it was cold, we had more demand in winter. Now we've built the system, we've built more wind. Basically, we don't care that much about temperature anymore. What we really care about is wind speed. So we've changed the weather that we're sensitive to. So looking for a fixed set of stress events doesn't make sense. So we need to start thinking about this in a much more integrated way. More generally, there are questions around, we have multiple different reconstructions of historic weather. What are the uncertainties that then produces when we convert into energy properties? What are the uncertainties in these conversion models anyway? We have different models for converting, estimating wind power from wind, for example. There are issues of resolution biases and deficiencies. No climate model is perfect. How do we deal with that? The fluctuations in climate on decadal timescales are very difficult to sample. How do we sample possible future climate projections? There's a whole issue around imperfect foresight. How predictable are we? The prediction of what the weather is going to do day ahead and how that feeds into the planning of the power system is something that hasn't really been dealt with. And one of the key barriers, to kind of cut a long story short, one of the barriers to studying this better is the feasibility of running very long power system simulations. So if you have a detailed power system model, my understanding is it's very difficult to scale up to do a 100-year simulation of weather and climate data to really start to probe weather and climate uncertainty. So this brings me to the kind of the worry I have with the data and the open data aspect, which I think in general is very good, but it does lead to a worry. The problem is that the climate data produces, it's enormous, it's terabyte, petabyte scale stuff. And you need tons of it to do standard uncertainty quantification metrics. What we want is kind of an estimate of what the power system is going to look like and some error bars on it that give you some idea of the uncertainty associated with, in this case, climate. And it just renders this problem intractable. And this particular is a figure that was presented at this workshop. I believe it comes to the Plan FRES project, and it was Professor Smoes who showed it at the workshop. This idea of there's this truckload of climate data there, but how do we get it into this tiny little folder that is the capacity of an energy system model to ingest it? So we need techniques to do this cleverly that samples it in a way that is safe from a climate perspective. And in my own group, this is something I've been working on with a student of mine, Aidan Hilbers, who's given a talk, who's given on the posters later, and I'd very much encourage you to see that. What we've been trying to do is develop use toy models of power systems to develop sampling techniques to bring that problem down in scale. So we've rendered problems that would take years to solve down into something that takes a few hours or days on a standard computer for a small scale model. So we're trying to develop techniques that bring that climate data into a more accessible regime, and I think there's a lot of work to do in this space. So I've probably spoken longer than I should do, so I'm going to conclude. But the core message I give over and over again is, for climate scientists, energy systems are more than just a set of weather inputs. They're more than just a set of fixed stress events that we know what they are. And the provision of high-resolution climate model data, high-quality climate model data, is vital for energy system modeling. And we really need to start to think about integrating what those users need into our assessment and our calibration of those climate models. On the other hand, speaking to the energy scientists, there's a tendency to think about climate as just a series of data, a bunch of statistical inputs that you just throw in safely into the model. The data is necessary, but in itself, it's not a sufficient way to address climate uncertainty. There are a lot of non-trivial challenges in making that data appropriate for its use. So, in my opinion, we just need to build bridges between these two communities, which brings us back to this workshop we ran. As I say, the shared and open models and data and the common language is absolutely vital. I'm not saying it's not vital and highly valuable, but it's not in itself sufficient for good research. It needs that engagement within the communities, and it needs a shared understanding of the issues, and in particular the data limitations, whether the data is capable of providing the information you need. And for that, you have to build these things together. So hopefully I've given you a bit of an overview of some of the things where I see an issue, and I'm very happy to take questions or be told that I'm completely out of order. So thank you very much.